Under this farmland lies one of the most important raw materials for the chemical industry, salt. This is Imperial Chemical Industries salt mine at Winsford in Cheshire. The Cheshire salt deposits are enormous, 60 kilometres by 24, 400 metres thick, 100 million tonnes of salt. Explosives are used to loosen the hard walls of rock salt. Natural rock salt is so strong that there's no need for any mechanical support in these vast man-made underground chambers. In goes the explosive. Huge machines are also used to cut into the walls of salt. The great lumps are crushed. Then conveyors take the coarsely crushed salt along miles of tunnel to machines which grind it even finer. Up it goes to the surface. Only a small proportion of the salt from the Cheshire salt field is mined as solid salt like this. This finely powdered salt, which is mixed with other materials, is going to be used mainly not in the chemical industry, but for removing ice and snow from icy roads in winter. Most of the Cheshire salt is brought up from under the farmland in a very different way, as brine, salt solution, through wellheads like this. This is one of the wellheads in the Cheshire salt field. They're all looked after from a central control building. There are about 90 wellheads, all pumping up salt solution from many metres below, creating underneath each a giant pear-shaped hollow which will be filled with saturated brine after the cavity has been developed to its maximum volume. Here's how the process works. 3 pipes, one inside the other, are sunk down into the rock salt. Water is pumped down this pipe. Air down this outer one. And the brine, salt solution, is forced up this central one. Here's an actual wellhead. This is where the water is forced down. The air pipe. And the brine up here and passes into the pipeline from the salt field. Several miles away, the brine from all the wells is collected in huge reservoirs. Hundreds of thousands of litres of concentrated salt solution, raw material for a very important part of the chemical industry. In that plant in the background, the brine is purified. Then it's conveyed through more pipelines to ICI Mons division at Runcorn in Cheshire, a great area of chemical plant producing many different substances from this raw material. There are the pipes bringing in the brine. Much of the brine is converted into alkali, sodium hydroxide, and chlorine gas in one very important part of the complex. These are some of the mercury cells in which the change is accomplished. These cells work by electrolysis, decomposing the brine with an electric current. Let's first of all examine the process in the laboratory. This is sodium chloride, salt solution, brine. We add an indicator, phenolphthalein, to the salt solution, then connect up the battery. The salt solution conducts electricity, and a pink colour develops around the cathode, the negative electrode, showing that an alkali is formed, and a gas bubbles off. Water dissociates into positive hydrogen ions and negative hydroxide ions. We've put a ring around the hydroxide. The positive hydrogen ions collect electrons from the cathode and hydrogen gas is produced. More water dissociates and negative hydroxide ions are left over. With the positive sodium ions from the salt, this gives us sodium hydroxide, an alkali, in solution around the cathode, hence the colour. There's also a gas given off around the anode, the positive electrode. We'll come back to this later. Another setup. The salt solution is in the trough. The cathode is a nickel spatula surrounded by a porous pot. The anode, the positive electrode, is a carbon rod, partly enclosed in glass tubing. Any gas produced here will pass out along a delivery tube. We connect up to a power supply and a current passes. As before, a gas bubbles off from around the cathode. The porous pot, to some extent, prevents the solution around the cathode from mixing with the solution in the rest of the trough. Once again, we can show that an alkali is formed here, this time using litmus paper. What about the gas coming from the positive electrode, the anode? Here, negative chloride ions from the salt give up electrons to the anodes and chlorine gas is formed. We can test for the chlorine. It's a gas which bleaches litmus paper. Watch. Finally, here's a lab setup which works like those mercury cells in the plant. This time, the cathode is a pool of mercury. It can be connected to the power supply through a copper wire enclosed in a length of glass tubing, passing down through the salt solution. The anode is again a carbon rod. When the current's flowing, you can't see much happening at the mercury cathode, but this time the positive sodium ions are being discharged. Each sodium ion picks up an electron, producing sodium metal. The sodium metal dissolves in the mercury to form sodium amalgam, NaHg. As before, negative chloride ions are discharged at the anode and chlorine is again given off. Let's disconnect our little mercury cell. If we now run off the sodium amalgam into water, it reacts. Sodium hydroxide solution is formed, hydrogen is given off, and the mercury is regenerated. Here's the sodium amalgam being run into water. You can see the tiny bubbles of hydrogen. And let's test for the presence of the alkali, sodium hydroxide. Yes, the litmus turns blue. The mercury cells used industrially look very different, but the principles on which they work are exactly the same. The cell has a steel base and the sides are lined with ebonite. The mercury runs down the sloping floor and is made the cathode again, the negative electrode. Purified brine, salt solution, is fed into the cell. There's a row of anodes, positive electrodes, made of titanium. Sodium is discharged at the cathode and forms sodium amalgam with the mercury. Chlorine gas is given off at the anodes and is piped off from the top of the cell. On the right, there's water in a vessel called a denuder. When the sodium amalgam runs down into this, sodium hydroxide solution is formed, hydrogen gas is given off, and mercury is regenerated and can be recirculated round the system. The point about using the mercury as cathode is that the chlorine and the alkali are produced quite separately so that they don't react with each other. There are several great rooms like this full of mercury cells. The cells run across the picture from left to right, mounted closely side by side. You can't see much happening, but chlorine and sodium hydroxide are being produced continuously, day and night, 7 days a week. Here are cells being stripped down for servicing. The mercury flows down the sloping floor of the cell. When it's in action, the steel floor will be completely covered. This is one of the anodes, made of titanium metal. It's lowered into place. Several of these will be fitted along the cell. It's important that the anodes don't actually touch the mercury which is streaming along the base of the cells, but they must be separated from it by only a matter of millimeters to keep the cells working as efficiently as possible. He's checking the distance between the anodes and mercury cathode electrically. He adjusts any anodes which are not quite at the right depth. In these cells, the sodium amalgam formed is streaming down towards us. Here's the denuder, containing water with which the amalgam will react. With the lid off, you can see the amalgam streaming in to react with the water. The denuder actually contains carbon balls immersed in the water. The reaction between the sodium amalgam and water occurs more vigorously at the surface of these balls than it would do if they were not present. The hydrogen is led off, some to be burned to provide power in the plant, some to be sold for use in various industries. Here, at the top of the cell, you can see where the brine is fed in. Beneath the cells is all the pumping gear and piping. That big yellow pipe carries off the chlorine, which will be used in the manufacture of many very important chemicals. In the control room, every cell can be monitored to make sure that all is going well. 197. This is an indication of the electrical current being used in this one set of mercury cells, 197,000 amps. The current is fed to the cells through bus bars made of aluminium, which is a very good electrical conductor. The production of chlorine and alkali, the chlor-alkali industry, uses enormous amounts of electricity. Here at Runcorn, the power consumed is actually 1% of the total electricity consumption in Britain as a whole. This indicates how important chlorine and to some extent sodium hydroxide are in the world today. This is a museum piece, one of the kinds of chlor-alkali cells which used to be used earlier in this century. Compare its size with the size of the cells in the plant today. But in fact, there are some cells today which are quite small and nearly as productive as these Mercury cells. These are diaphragm cells, each producing up to 2/3 of the chlorine and alkali from brine as the big Mercury cells. They don't use mercury cathodes. Instead, they keep the chlorine and sodium hydroxide they produce separate using a quite different technique. Porous diaphragms between the electrodes, the anodes and cathodes, which to some extent keep the alkali away from the chlorine. There's one of the complex diaphragm assemblies. Remember this? We kept the alkali formed around the cathode separate from the chlorine using a porous pot. Industrial diaphragm cells use the same principle, but they're just a bit more complicated. And here's yet another sort of electrolytic cell for making chlorine and alkali from brine, membrane cells. These are smaller still and just as productive as the diaphragm cells. In these cells, the anodes and cathodes are separated by thin membranes which only allow certain ions through, so that there's no possibility of alkali seeping through to the chlorine produced at the anodes. Each cell is a sort of many-layered sandwich of electrodes and membranes. Here's an experimental cell in the laboratory with just one section of sandwich. This is the cathode side, where alkali is produced and hydrogen bubbles off. Looking at the edges, the thin plastic membrane is in here, between two gaskets which keep the liquid in. And at the other side, the positive anode side, we can see chlorine bubbling off. The membrane cell is the latest in chlor-alkali technology, useful for large-scale or small-scale production of chlorine and alkali. Scientists are always working to make processes more efficient, cheaper to run. Here are the research laboratories of the Mond division of ICI in Cheshire. This is Ludwig Mond, one of the great pioneers of the chemical industry. The chemical plant at Runcorn was first sited there because of the rich salt deposits under these Cheshire fields. Today, production continues, using techniques which change as chemical technology progresses, making important chemical substances from that simplest of compounds, sodium and salt.